Okay, so as I mentioned last time, today is going to be the last kind of general, broad string theory review to get everyone up to speed and on the same page before we get into the more mathematical things, and also the connections with more modern research in lectures 3 and 4. But before I get to the main subject of today, which is going to be a bit of worldsheet review on the basic superstring theories, and then just going over some general statements about compactification and dualities, I wanted to pick up where I left off last time, or in particular, go back a little bit and make a few remarks about BRST quantization of string theory, which I'll kind of frame in the context of the closed bosonic string. But the reason I'm reviewing BRST quantization is just because I want to stress to you the formal similarity of BRST quantization and what goes into that, and so much of importance in modern mathematical physics. Like I said, if you had to summarize these lectures in one word, the takeaway is cohomology. BRST quantization is all about cohomology. Something called twisting or topological twisting, which is completely ubiquitous in mathematical physics, is all about cohomology. And so if you remember your BRST quantization from your gauge theory section of QFT class, then you're ready to go and go forth and do research on mathematical string dualities, really. So I just want to remind you briefly of that. Okay, so let me denote all of the fields. So BRST, refresher. So what's the basic idea? Let me denote all of the fields in whatever path integral I'm interested in, string theory or whatever, by phi sub I, where I'm using a condensed notation that's pretty common in the BRST community, where I doesn't just label the species, it also is a shorthand for the space-time dependence. So in the bosonic string case, I also includes the dependence on sigma and t, and the gauge symmetries that we're talking about in particular can include diffeomorphisms. As they do for string theory. And we're going to assume, so these are our fields, including their space-time dependence. And here by space-time dependence, I mean, in our case, the world sheet for a general quantum field theory, whatever your space-time coordinates are. And let's assume that the gauge variations satisfy an algebra, where again, the indices are incorporating secretly the dependence on any coordinates. So these are the gauge variations. And for the purposes of today, I'll assume that the structure constants of this Lie algebra that's generated by the gauge symmetries are independent of the fields in my theory, and that these gauge variations do not require imposition of the equations of motion. It's an off-shell statement, and the structure constants are really constants. And in general, and indeed in mathematical physics, we often want to relax those conditions. And if we want to relax those conditions, we need to do something a little bit fancier and go to what's called the BV, Baddelin-Vilkovisky formalism. And so that is really, the godfather of covariant quantization procedures. Again, it's completely based on cohomology type stuff, so it's not so much that's new, but I'm not going to talk about it today. But you will see it, for example, in discussions of dealing with string field theory and various other sort of more high-powered gauge theory problems. So that's just a kind of remark for culture. Okay, and so we have some gauge symmetries, and the goal is to impose some set of gauge fixing conditions that are given by some system of equations. And normally how this goes is you use the Faddeev-Popov procedure, which I cheated a little bit by putting in your background reading to remind you of how the Faddeev-Popov ghosts and all of that sort of come about. But the basic idea is that this whole quantization procedure is going to have the effect of kind of dividing out by an extra volume of the group of gauge symmetries that is kind of tucked away in your path integral measure, and you want to get rid of it. Because what we really want to do is to integrate over each gauge equivalence class of all our fields once and only once. So we're just removing redundancies here. So just to be concrete about what we talked about last time, let's denote the gauge transformation of my auxiliary worldsheet metric by G epsilon, where epsilon is going to be it's going to denote a gauge transformation. So a diff cross Weil transformation of the closed bosonic string. So again, we saw this last time. A general diff cross Weil thing. You guys know the indices, so I'll just kind of be super sloppy. Just denoting a general gauge transformation of my metric there. And the idea is that we want to use our gauge transformations to bring the metric into some gauge fixed fiducial metric that I'm calling G hat of epsilon, that we can achieve by some transformation epsilon. For example, this could be our flat gauge metric. And then the Faddeev-Popov measure is defined by, a very fancy way of writing 1. So we want to insert this kind of delta function into our path integral with a suitable integral over the gauge group, whose measure I'm not going to make precise. And the Faddeev-Popov determinant is the thing that multiplies it, such that I actually just have the identity on one side. And the idea is that in the path integral, when we integrate over little g, we'll be fixing the value of the metric to our fiducial metric G hat epsilon. And the integral over epsilon, when we insert it into our path integral, is going to produce a factor of the volume of the gauge group itself, which is going to cancel out the piece that we didn't want in our original path integral. And it'll do this because the Faddeev-Popov determinant and the action and the measure are all, by assumption or construction, gauge invariant themselves. So at the end of the day, we'll integrate over the delta function, and the path integral will be something like this, where again, I haven't explicitly written down what the Faddeev-Popov determinant is, but all of my G's have now become G hats. And then I'll remind you that there's a nice way to rewrite the Faddeev-Popov determinant in a path integral form, using tricks from Grassmann integration and various identities therein. And that involves supplementing the original action by a gauge fixing condition and a Faddeev-Popov action. And this leads to the introduction of the Faddeev-Popov ghost that I think many of you probably remember. So our Polyakov action is going to become the Polyakov action plus some gauge fixing action plus a Faddeev-Popov action at the cost of introducing new ghost and anti-ghost fields and a Lagrange multiplier field. So the gauge fixing part of the action is just, as simple as can be. You're just introducing some non-dynamical field whose role in life is to be a Lagrange multiplier for the gauge fixing constraints that we want to impose on all of our fields. And so this part rewrites the delta function that I already integrated out in the previous line. But if we want to be super general, before we integrate out the delta function, we can just rewrite it like so. And then the Faddeev-Popov ghosts come in this way. So in total, if you want to rewrite the path integral, including this Faddeev-Popov piece, you're going to have something that involves an integral over all of our original fields. So here I'm reverting a bit to the generic notation, an integral over the Lagrange multiplier field, which is trivial because it, just appears linearly, and integrals over the ghosts over this total action. Right. So we have some path integral representation of the gauge fixing delta function, and we have a path integral representation of this Faddeev-Popov determinant. And again, I won't prove that that this is the correct thing, but hopefully you guys remember it from quantizing Yang-Mills theory or something like that from your courses.
Is the whole thing still gauge invariant? Is S total still gauge invariant?
Good. And in fact, this is a great question to lead into my next comment about how what we've done is to now replace gauge symmetry in a sense with a new symmetry called the BRST symmetry. And everything is invariant under the BRST symmetry, as I will get to right now. But yes, the Faddeev-Popov metric is gauge invariant, the determinant, the action, everything.
Okay, thanks. Yeah.
Good. So Now we can do these integrals and gauge fix the action. But this gauge fixed action, which now includes the Faddeev-Popov ghosts, replaces the gauge symmetry now by the BRST symmetry. So the BRST symmetry is our new avatar of gauge invariance, under which everything is going to be manifestly invariant. So I'll call the BRST symmetry delta B, which, if you like, classically acts on fields with some BRST charge that I call Q. So classically, this is some Poisson bracket, and in the quantum theory, we'll hope to promote it with a commutator and anti-commutator with respect to some BRST operator Q. And the BRST symmetry is now a global fermionic symmetry. So in particular, it satisfies del B squared equals 0. And the fancy word for this is nilpotent. And once we have a nilpotent thing, just like in, ordinary cohomology, de Rham cohomology, if you have a nilpotent thing, you're sort of in business. You can start thinking about cohomology. But just to be explicit, the BRST operator acts on everything like so. So the ghosts, the C ghosts provide a fermionic, now an anti-commuting representation of our gauge parameters and how they act on the field. This Lagrange multiplier field is trivial, but it's related to the anti-ghost under this transformation. And the ghosts themselves satisfy the gauge algebra. Okay, and by construction, the gauge fixing plus ghost part of the action can be written as a total derivative with respect to the BRST symmetry. It's a BRST variation. So the total action is BRST invariant. The original action, the Polyakov action, is BRST invariant because it was already gauge invariant. And this new thing is BRST trivial, so the total action is also BRST trivial, or BRST invariant, excuse me. So the BRST symmetry, it might be a fermionic symmetry, but who cares? It's a symmetry. And that means we can construct a Noether current using the Noether procedure and a corresponding conserved charge. I won't do all of that explicitly today. And furthermore, if our path integral measure is invariant under the BRST symmetry, then we can promote this classical BRST charge Q to a Hermitian quantum operator that acts on the Hilbert space and perform quantization of our theory with that gadget instead. And if we let's assume that our path integral measure is invariant, then what one does is to define physical states to be those that are Q closed. So physical states in this BRST framework, by definition, are Q closed. They're annihilated by the BRST charge. And if you have this condition, then any transition amplitude between two physical states is going to be invariant under small variations of the gauge fixing condition. So let me abstractly write some transition amplitude like this and denote delta as a little change in the gauge fixing condition. Well, then all this does is bring down this piece of the action, which by construction is delta B of something, which I can write then as a suitable anti-commutator of the BRST charge with that thing. Delta, again, is just a little variation of the gauge fixing condition. And this now has to be 0, because if I expand things out, then Q is going to be acting on the initial and final states, and by definition, it's annihilating them. And that's good, because we don't want any physical quantity to depend on our choice of gauge fixing. We should be able to deform it at least infinitesimally. I mean, maybe there's subtleties if you try to take radical limits, but for small changes, at least this is good. And as a Hermitian operator, one can further show quantumly as well that this BRST charge is also nilpotent, which you can prove by demanding that it commutes with this corresponding change in the Hamiltonian that comes from changing the gauge fixing condition, and demand that it remains a conserved charge. So physical states are Q closed. But in addition, shifting a physical state by a Q exact state can have no effect on physical amplitudes, or in a more CFT context, on correlation functions, depending on what sort of observables we're going to compute. So Q, and I'll show that in a second. Or actually, I I don't need to show it because I've essentially already showed it on this line, right? Anything Q exact that appears in an amplitude or a correlation function is going to be written as Q of something. I again can expand out the commutator or anti-commutator, and Q is going to annihilate the physical states. So clearly, if I shift a physical state by some Q exact piece, that's Q of something, and the same argument shows that Q exact states are going to decouple. So Q exact states have no effect. And that means that in this way of covariantly quantizing things, we can identify our physical Hilbert space with BRST cohomology. And similarly, if you prefer to think of correlation functions, I can assume that the BRST symmetry preserves the vacuum, and I'll have correlation functions, say, in the vacuum of a bunch of Q-closed operators, and the same arguments go through identically to what I just wrote down. Okay, so now I can write this down a little bit more explicitly for the closed bosonic string. But I do want to make sure I get to some of the newer stuff today. So in the typed up notes, there would be more details. Anyway, what I would briefly mention is that if we went through this kind of procedure for the closed bosonic string, so far what I've said assumes that the measure is invariant under the BRST symmetry. And in the case of the closed bosonic string, another way to derive the critical dimension is actually to demand cancellation of a Weil anomaly that appears when one studies the transformation of the measure by a general gauge symmetry. There's actually any UV regulator for the path integral can be chosen. It turns out to be diffeomorphism invariant, but it will have a Weil anomaly. And that anomaly also is proportional to d-26 in the closed bosonic string. So that's another way that the critical dimension comes up. But I won't go through the details, I think, in view of time. But yeah, there will be more details in the notes about that. I just kind of want to stress this general idea of BRST cohomology and restricting to the space of physical states from that point of view. And it's nice because this is a purely covariant thing. I haven't had to make any funny choices in Brake-Lorentz invariance. And there are various proofs that show the equivalence of BRST quantization to light cone quantization, at least modulo some subtleties. There are some cases where you just really don't want to use light cone quantization. You really do want to use BRST quantization. So for certain specialized purposes, it's really the correct thing to do, particularly when one has to deal with things like subtleties of zero momentum states in string theory. So that's just kind of the takeaway message that I want to leave you with before I move on to the main subject of today. Any questions or concerns about that before I move to superstrings and kind of do an overview of compactifications? All good? Okay. Yeah, hopefully some of this, I mean, the particular formulas for the closed string are instructive and fun to go through. Like I said in the typed up notes, I'll certainly have more equations and details there, but hopefully the basic idea is familiar. And my goal in these lectures is to really kind of hammer home that if you have a few basic ideas, like restricting to cohomology of some fermionic symmetry, not only is it a really useful thing to do, but actually it's kind of the conceptual underpinning of just a huge amount of modern mathematical string theory research and quantum field theory research. So it can really take you a long way if you start feeling comfortable with these concepts. Okay, so now we'll go to the main part of today's topic, just superstrings and compactifications. And so today I just kind of want to give you a little bit of a flavor of some of the vast web of string dualities when you start compactifying on non-trivial manifolds. I also have a section in my typed up notes that I haven't posted yet on just 10-dimensional dualities, where you saw an example of that with type 2A and M theory in the previous lecture. But since it's logically disconnected from the rest of the lecture series, I probably won't get to honest 10-dimensional dualities. But if you've never seen them before, ask me in Slack, in GatherTown, check out the notes. If you've ever been confused about statements, about like the S-duality of heterotic strings, feel free to ask me. I just probably won't have time to touch on those things. I'll focus on dualities that come from compactifications on non-trivial manifolds today. And that should also fit in well with Irene's lectures tomorrow. I'm hoping to mention mirror symmetry as kind of a primary example of an interesting compactified duality today. And just make some basic statements. Okay. So I obviously can't cover everything that I'd like to in 4 lectures. And we exhaustively went through a bunch of worldsheet stuff yesterday. So today I'm going to mention a little bit how the analogous kind of worldsheet thing would go for superstrings, just remind you of the superstrings and where they come from by appealing to the worldsheet technology we thought about last time. And then basically propose various results about dualities and compactifications. And those I won't be able to really derive for you exhaustively, or so some of the statements might look a little bit mysterious. And if you want more details on where they come from, again, please feel free to use Slack, use GatherTown, ask me afterwards, whatever you like. Okay, so for superstrings, we're going to add to our fields on the worldsheet some fermionic superpartners. So they are worldsheet spinners, but they are space-time vectors because supersymmetry has to commute with all global symmetries, and the space-time Poincare symmetry is a global symmetry from the point of view of the worldsheet. And we're also going to give our metric some gravitino superpartners as well. So we're adding some supersymmetry on the worldsheet. It does not mean that we will automatically get supersymmetry in space-time, but for the string theories that we're studying today, they will also have space-time supersymmetry. And again, for subtle and more interesting cases, feel free to ask me anytime. So a lot of the basic discussion we had last time about our gauge fixing, splitting into left and right moving parts, say doing light cone quantization, level matching, all of that basically goes through with very little modification in this case, except of course we have now a critical dimension of 10 instead of 26. The Hamiltonian is going to acquire some standard fermionic terms because we're going to have extra fermionic oscillators. And ultimately you're going to end up with a Hamiltonian describing d-2 free fermionic degrees of freedom that I'll just label as psi upper I, that are superpartners to the free bosons that we had last time. Okay, and there's 5 basic superstring theories that can arise from this modification, and I'll review them each very briefly in turn. We have type 2a, type 2b, type 1, and the E8, cross E8, and SO32 heterotic strings. So again, for many of you, this may be boring, and just feel free to just chill out for the rest of the lecture. But if you've never seen these things before, I feel that it is my responsibility to you to say a few more words about them. Okay, so the fermionic fields also have a mode expansion in terms of free oscillators, and they have one essential novelty relative to the bosonic case is that you have 2 options for periodicities of the fermionic fields. And again, I'm sticking with a closed string today, but in particular, when you go around the closed string, I have the option of picking up a plus or a minus sign, as we know about fermions. So the choice of the minus sign, of course, is called the Neveu-Schwarz periodicity condition, and the plus sign is the Ramond periodicity condition. So when you combine, and this choice can be made independently on the left and right movers. So when you combine them together, they're going to have 4 sectors in your string theory to play with. And what these choices will do is change the moding in the oscillator expansion. So let me just write the left moving part because the right moving part is identical. So here is for the Neveu-Schwarz, where I'm summing over integers, but everything is shifted by a half. So this is a half integer moding. And they have the usual canonical commutation relations. And let me define also the fermionic contribution from the NS sector to the oscillator number. We had the bosonic oscillator number appearing last time and contributing to the mass shell formula and the Hamiltonian. And of course, the fermionic states have the analogous contribution that I'm sure you've essentially seen before, perhaps in other context. So in the NS sector, you can proceed, you can define an NS sector vacuum and do the same thing we did last time and build up the Hilbert space by acting with the bosonic and fermionic creation operators on the vacuum in all possible ways. And now that we have fermions, the lowest lying states are just going to be the fermions acting on the vacuum like so. And these transform as a vector of SO8. So I'll denote that by 8 vector, because of course they have a vector index. The Ramon sector is very similar, except I have integer grading instead of half integer grading. And in particular, that means periodic boundary conditions with their integer moding allow for the presence of 0 modes. So I won't recopy the formula, but just get rid of those factors of a half for the Ramon sector. And let me just write the oscillator number out to be completely explicit. Very similar. And there are also slightly different 0-point energies in the NS and R sectors, and I didn't compute 0-point energies in the bosonic case, and I won't do it this time, but I will just write their contributions to the mass shell formula. And again, I'll just write down the left moving parts, and the right moving parts, put tildes all over everything. So different 0-point energies. And so in the Ramon sector, you'd want to, again, do the same thing, act on the Hilbert space, but we have fermionic 0 modes, and they're the only subtlety relative to the NS sector. So the ground states have to form a representation of this Clifford algebra that the 0 modes are furnishing. And I won't go over the construction. It's not too complicated, but roughly speaking, the 0 modes are behaving like Dirac matrices for the SO8 symmetry group, and they act on the ground states. So you might expect a priori that the Ramon ground states transform like some kind of SO8 spinner, and indeed they do. And again, I'm going to skip the construction, but they turn out to transform as a 16-component spinner of SO8, and that representation is reducible into 2 8-component spinners of opposite chirality, which I'll just call 8S and 8C, spinner and conjugate. And because the Ramon ground state transforms spinorially with respect to spacetime, say from the left, and again, analogously on the right, then this is an easy way to see that fermionic states in spacetime come from RNS and NSR sectors, because we have a bosonic and times a fermionic thing, and the bosonic states come from RR and NSNS when we combine the left and right moving pieces together. And sort of the last novelty that we need to talk about the superstring theories is everyone's favorite thing, the GSO projection. And again, in view of time and technology and everything like that, I don't have time to do a full exposition of the GSO projection and why it comes about, but the basic idea is the following. And it involves the fermion parity operator -1 to the F that acts with a -1 on the fermions and a +1 on the bosons. And this, the fermion parity operator should be regarded as a discrete gauge symmetry on the world sheet. It's not a continuous one like the diff cross Weil, but it is a gauge symmetry. It's a Z2 gauge symmetry on the world sheet. And in particular, one can also regard the left and right moving fermion parity operators separately themselves as discrete gauge symmetries on the world sheet. And so what do we do when we think about physical theories with some gauge symmetry? We want to make sure that we're projecting onto gauge invariant configurations. So roughly speaking, in our path integral, we're going to expect that we're going to pick up suitable projection operators onto states of definite fermion parity. This is a projection onto a discrete, projection for a discrete gauge symmetry. Okay, so which sign comes up and why? To go into more detail, we need to impose some additional consistency conditions that I didn't talk about in the bosonic string case, but that also would appear there. But happily, you guys have seen it in your CFT lectures and in other places, and that's the imposition of modular invariance. So we get another string theory consistency condition by considering the vacuum amplitude of the vacuum amplitude of string theory at genus 1. At genus 0, it turns out we don't get any additional constraints. But you guys know we've been talking about conformal theories on the world sheet. In particular, that would be more obvious if I did a proper covariant quantization of string theory. But we know that in addition to the local diff cross Weyl transformations that I use to fix the metric into flat gauge, on a world sheet of non-trivial topology, I can also have large diffeomorphisms, gauge symmetries that are not connected infinitesimally to the identity, like the other ones that I use to fix the metric into flat gauge. And large diffeomorphisms of the torus form the group SL2Z, which you all have seen before many, many times. And as you also already know, these groups sometimes go by the horrifying name of global gauge symmetries, but they're gauge symmetries. And we need to have a diffeomorphism invariant theory. And what modular invariance does in the superstring is it not only mixes up the NS and R sectors when we are combining all the left and right movers as well, but it's mixing those with the introduction or not of this fermion parity operator. So ultimately, when we compute modular invariant partition functions, having a modular invariant partition function in my string theory is once I have NS and R sectors, I'm going to start getting these factors of -1 to the F in the game. And you can see that pretty easily with explicit computations that unfortunately I just don't have time for. But the result of that is the following thing. In the NS sector, the fermionic oscillator number it can be integral or half integral. And it turns out that the consistent choice is to keep half integral states and implement the projection with the minus sign. And again, you can see this pretty easily from a computation that unfortunately I don't have time for. But in the R sector, you have these spinorial ground states. Both choices of GSO projection for both of these signs turn out to be consistent with modular invariance. And they result in projecting on states of a definite chirality, a spinor of definite chirality. So then when you combine the left and right movers together, so the NS just has one choice, the R sector can have both signs of GSO projection, and now we build up a fully consistent thing by gluing left and right movers together, then the two options are that the GSO projection on the left and right movers can be the same, which leads in the R sector to ground states of the same chirality. And that leads to a chiral string theory called type 2B. Or the GSO projection in the left and right can be opposite. And that leads to ground states with the opposite chirality. And when you have spinors of both chirality, you end up with a non-chiral theory called type 2A. So they differ by the sign of the GSO projection, relative sign of the GSO projection. And when the dust settles, let me write down the massless spectrum for you that comes again from acting on the Hilbert space with the oscillators of lowest moding, imposing level matching condition, and also asking which of the states doing my Hilbert space trickery survive the GSO projection as well. So here's for 2B, the lowest lying states, the massless spectra. And in particular, this thing here with the NS sector projects out the tachyon. If I'm keeping states of half integral moding, the tachyon gets killed. That's one of the reasons we like these GSO projections. So from the NS sector, let me kind of denote things as coming from the left and the right, and then I'll list what Tendy fields they correspond to. So in the NS sector, I just have my 8 vectors on the left and right coming from those psi to the minus halves, and those ultimately yield our old friends, dilaton metric and B field. In NSR, we get some fermions. So type 2B only has one chirality of spinor. And those are fermions that I won't bother writing down because, you know, a little bit less interesting. I'm happy to write them down in more detail if I get questions after. And the Ramon sector is going to produce some additional interesting bosonic fields. In particular, we get as it turns out, antisymmetric p-form fields for even p. And it turns out that this 4-form field strength rather famously is self-dual, or the famous 5-form self-dual field strength in type 2b, though I won't derive that fact today. Something very similar happens for 2a, except for 2a, you can go through the same exercise. In particular, in the Ramon sector, we'll have opposite chirality of spinors. And at the end of the day, p-form fields with odd p. And also in 2a, from the NS and RNS sectors, we'll have fermions of both chiralities present. In the 2b, the fermionic fields that I didn't write down are of the same chirality, copies of things that are the same chirality. So both type 2a and 2b still have diffeomorphism symmetries and the gauge symmetries coming from the B field, just like in the bosonic string case. But all of these p-form fields also have gauge symmetries. And as you already know from many other contexts, the D branes are going to be the charged objects under these antisymmetric p-form fields. And both type 2a and 2b do have space-time symmetry. Again, I won't go through the proof that GSO projecting in this particular way translates worldsheet symmetry to worldsheet supersymmetry to space-time supersymmetry, though it turns out to be true. Both of them have 32 supercharges arranged into 16 component spinors of definite chirality. They have the opposite chirality in 2a and the same chirality in 2b. Okay. So that was type 2a and 2b. There's type 1, which I'm going to be brief about because it's messier and more complicated than the other ones, and I just don't like it as much. A shortcut to obtain the type 1 string from what we have so far is to notice that the type 2b string in 10 dimensions has completely identical left and right moving degrees of freedom. So there's an obvious symmetry where we just exchange the left and right movers in type 2b. And whenever you have a symmetry, you can ask about theories that come from quotienting by that discrete symmetry. And this is called the orientifold symmetry. It's an involution. And it's called that because it reverses the orientation of the string worldsheet. So that means in particular that you end up with unoriented string theories, which I didn't even tell you about at all, and you have to deal with the complications that come from that. It means you get unoriented worldsheets like the Mobius strip or the Klein bottle also coming into play in your perturbation expansion. And it turns out that if you look at the states from 2b that survive that Orientifold projection, you still get the graviton and the dilaton from the NSNS sector, but in the RR sector, the antisymmetric the antisymmetric components of the 2-form field survive. So the antisymmetric part. And this is the origin of the B field in type 1. So it actually comes from the Ramon sector of type 2, and so I'm calling it C instead of B. It turns out that there is an additional complication in type 1. There's a divergence. From a space-time point of view, there's actually an uncanceled Ramon charge in the vacuum, or a tadpole, or various ways to see the fact that there's some kind of anomaly in these theories. You can also see it from the worldsheet by dealing with unoriented things. But it needs to be canceled. And it turns out that this cancellation only occurs if you additionally add an unoriented open string sector. And it further turns out that this only happens for an SO32 gauge symmetry. So there's additional gauge fields in type 1, and you need them to cancel a space-time anomaly. So that also, that's the massless bosonic degrees of freedom in type 1. And as just a, again, remark for culture, anomaly cancellation via coupling open and closed string sectors together is a very powerful tool. It turns out to also be true in the topological string theory, which we'll meet in the subsequent lectures. Anomaly cancellation works beautifully in the topological string, and it's related to a mathematical idea known as Cazul duality, which is a modern area of research, including something that I've been working on. And in a semi-recent paper by Costello and Lee, they explained how an anomaly cancellation via coupling of open and closed sectors of the type 1 string theory works in this topological string context and its connections to mathematics. So unfortunately, that's a mathematical thing I won't have time to tell you about in these lectures, but just something for you to have in mind. Okay, so finally, there's the heterotic string. And the heterotic string takes advantage of the fact that in closed strings, left and right moving degrees of freedom are basically completely decoupled. So you can have some bosonic stuff on, say, the left and supersymmetric stuff on the right. So in particular, it will have 24 scalars on the left, 8 scalars, and 8 fermions on the right, if we just kind of repeat the same analysis I did in the last lecture. So what do we do with the extra 16 bosons? It's a bit weird. So what if you imagine that they came from 16 honest bosons with both left and right moving modes, and you demand that somehow we kill all of the right moving degrees of freedom of these extra 16 bosons, then setting those to 0 forces you to set the center of mass modes and the oscillators to 0. And it forces you to fix these circles. Excuse me. So if we want to kill the the left moving bosonic degrees of freedom, what we want to kind of do is imagine, if you will, that they are compactified on some 16-dimensional space, and also we've somehow killed the right movers. And if you try to do this, if you start from an honest toroidal compactification of 16 scalars and try to somehow kill the right movers, so you have some non-geometric thing, then this forces the radii of all of those extra compactified directions to be frozen at the string scale. That's kind of a heuristic way to think about what's going on with these extra 16 degrees of freedom on the left in the heterotic string. And modular invariance comes back in the heterotic string and imposes constraints. For example, on the center of mass momentum modes of these left-moving scalars. It turns out that modular invariance dictates that these center of mass modes, where I goes from 1 to 16, have to live in what's called an even self-dual lattice, a 16-dimensional even self-dual lattice. Even means that the square length of all of these vectors is even. Self-dual just means that any vector in the lattice that has an integral product any vector that has an integral product with all of the vectors in the lattice sits in the lattice itself. So the dual of the lattice is the lattice itself. It's self-dual. So this comes from modular invariance. Good. And if you wanted a 16-dimensional even self-dual lattice, you have only 2 choices, the so-called E8 cross E8 and SO32 lattices. In the interest of time, I will not write down the lattice vectors, but it's pretty easy to do. And so we have 2 options that satisfy modular invariance in this heterotic string. And we can canonically quantize just as before and impose the level matching condition. Again, the right movers have the option of being in NS and R sectors. So we also need to GSO project, because modular invariance will again mix up NS and R sectors with suitable fermion parity operators. So that comes into play too. And the states surviving the level matching condition and the GSO projection are as follows. So from the NS sector, well, we have the dilaton, metric, and B field as before. Also from the NS sector, we can act with an oscillator, a bosonic oscillator of degree of moding -1 for all of these 16 I's. That leads additionally to some gauge fields. And these gauge fields turn out to form an abelian group U1 to the 16. So we get the Cartan part of the symmetry group from the corresponding lattice. But from the NS sector, you could also, it turns out that there's another massless state. Remember that the vacuum is an eigenvector under the momentum operator. It has some momentum. And if I denote that by P, then for vectors where P squared equals 2, the so-called roots of the lattice, this turns out to still be a massless state. And they also give some additional gauge fields. And those gauge fields will, corresponding to the root lattice of the 2 possible lattices, will combine to ultimately give a non-abelian gauge symmetry, either an E8 cross E8 gauge symmetry or an SO32 gauge symmetry. And similarly in the R sector, we can have the same combinations tensored with the spinor on the right to get some fermions, and also this combination to get even more fermions, but let's ignore the fermions. So the type 1n heterotic string theories with their corresponding GSO projections have n equals 1 supersymmetry in 10D spacetime, half as much as the type 2 theories had. So there are 16 supercharges that form a 10-dimensional spinor. And if I had time to rearrange all of the massless fields into appropriate multiplets of the corresponding supersymmetry algebras, you'd see that this works out. So now I have a half hour and I want to tell you about some simple compactifications and dualities, and I'll try to get through as much as I can while still being hopefully comprehensible. Okay, so we have our string theories and we know what we want to do. And in particular, if we want to have any tools by which to compute with, at least perturbatively, we know that we're going to remember one of our effective expansion parameters. So of course, we have the string coupling. We're going to assume that to be weak throughout everything I'm going to say. And we have our other expansion parameter that's alpha prime over L squared, or last time I called it R squared, which is some length, which is a suitable characteristic length scale associated with the scale of variation of the field fluctuations. So you can think about it like a suitable curvature radius in space-time. And when we're compactifying, we'll think of this dimension as the size of the compactification manifold X. So we're assuming that X is sufficient, the volume of X as appears in this parameter is sufficiently large so that alpha prime over kind of the effective length scale is small. And also, you know, often we're studying at low energies as well. If we want to describe the compactified theory by a nice effective supergravity theory in the remaining dimensions. And unfortunately, you can try to get me to write down supergravity actions, but good luck to you. I like the world sheet better, or you can ask me later. Okay, so for a generic compact manifold, all the nice supersymmetry that we had in any of our parent 10D superstrings will be completely broken. And we're not going to study this case, not because it's not interesting, it's extremely interesting, but string perturbation theory is going to break down somewhat if we try to do this. We need better tools because it turns out—
clarification question.
Yes.
Sorry. What does the perturbation theory in G string correspond to? Like, is it like you're assuming G string is small?
I'm assuming G string is small. That means I'm ignoring all quantum gravity effects. So yeah.
In terms of string perturbation theory, does it mean you're only considering sphere amplitudes or no?
Yeah, I'm starting at genus 0 on the world sheet.
Okay.
And what I'll do next time in the topological string, already I'll actually get a huge number of interesting mathematics also from genus 0 on the world sheet. But keeping track ultimately of the stringy corrections from the alpha prime expansion is still going to be extremely interesting. And you can still get perturbative and non-perturbative corrections in alpha prime as well. Those will come up later on.
Okay, thanks.
Mm-hmm. But that's right, we're restricting to genus 0 on the world sheet. Good. So we're not going to consider a generic compact manifold because that's going to break supersymmetry and destabilize our Minkowski solution. I'm assuming Minkowski space-time over here. So I want some compactification manifold that's non-generic and preserves some amount of supersymmetry. And, you know, supersymmetry transformations come along, say, with some 10-dimensional spinor parameter in 10D, where this is just some generic supercharge. And instead, I have some compactification where the things are going to split, say, I don't know, 4 and 6 dimensions, or more general pairs of dimensions. And to preserve supersymmetry, you know, the action is going to have some terms that are covariant derivatives of these spinors. And these spinors, when they're constant, will correspond to some global supersymmetry transformations. And so you want to ask that a manifold admits some covariantly constant spinors so that this supersymmetry variation is 0, so that the compactification preserves some amount of supersymmetry. Because we want some a spinner, both a flat space and this internal space factor here. So the manifolds that admit such covariantly constant spinners, which will correspond to our unbroken supercharges in the compactified geometry, are the so-called manifolds of special holonomy. That means the holonomy group on some D manifold endowed with the standard Levi-Civita connection is a proper subgroup of the generic holonomy group, SOD. That's related to the condition of covariant constant spinners being allowed. And these manifolds have been classified, and some of the important examples that we see in string theory are, of course, D-dimensional tori, which have trivial holonomy, so-called Calabi-Yau D-folds, which have SUD holonomy. Sometimes we're interested in 4n dimensional manifolds with SPN holonomy, called hyperkähler. Those actually preserve even more supersymmetry. There are some interesting 7-dimensional manifolds with G2 holonomy, and some interesting 8-dimensional manifolds with spin 7 holonomy. So these are sort of the heavy hitters as far as the manifolds appearing in string compactifications. So we've met circles, 2-dimensional tori. I'm mostly going to stick to even dimensions. In 4 dimensions, there's of course a 4 torus, but there's also a unique Calabi-Yau twofold, whose holonomy then is SU2, which is isomorphic to SP1, so it's also hyperkähler, and that's called a K3 surface. It's a manifold with a unique topological type. It's very dear to my heart. I will not say anything about K3 compactifications today just because I don't have the time, but if you're interested, please ask me afterwards. And K3 manifolds are, again, ubiquitous in the web of string dualities. Today we'll focus on tori and Calabi-Yau threefolds. Yeah, go ahead.
So imagine that I don't make any reference to D3 branes, and I say I want to compactify type 2B on ADS5 times S5. Is there a way to see how many supersymmetries that would have?
A priori, that's if you don't have fluxes, this is not what you want to do to obtain a supersymmetry preserving compactification. Yeah, I have more stuff that I want to say to answer this question, but I think it would take us too far afield.
Okay, yeah, that's fine. No.
I mean, just to throw out, you can simply count the solutions to this killing spinner equation suitably modified. It's not just the covariant derivative of epsilon. There's also a gamma matrix times epsilon term in ADS5 cross S5.
Yeah.
But
I was just looking for some kind of a holonomy argument. But yeah, I guess it's a different language for the same thing.
Yeah. Good. Okay. So today we'll focus on tori and Calabi-Yau threefolds. And toroidal compactifications, completely analogously to the circle we saw last time, can be carried out in string theories totally explicitly. I mean, we basically have free field theory. We can go nuts. In general, as we talked about last time, if we're compactifying a string theory on a manifold with some more complicated metric, the worldsheet theory is in general highly interacting, and we're usually forced to work in this alpha prime, very small approximation. There are special examples where the worldsheet, even if you're on a non-trivial manifold, you can have, the worldsheet might, by some magic or special properties, be integrable or have some special symmetries that still make it solvable. For example, there are points like Gepner models in these kinds of moduli spaces that don't have a nice geometric description. They live on the same moduli space as Calabi-Yau compactifications, but the worldsheet theory can be very explicitly dealt with. And I won't have time to talk about those models today, but I do want you to be aware that sometimes in the right region of parameter space, you can still get lucky and have a world sheet with a lot of extra symmetry that you can do more detailed computation with, where you don't have to work in perturbation theory and alpha prime. So those do exist. They're nice and special. Tori exist. They're special. In general, we have to work perturbatively. So let me just quickly define a Calabi-Yau D-fold for you, if you've never really thought about these things before. So they're a special class of so-called Kähler manifolds with complex dimension D. So threefold means 6-dimensional. And they satisfy a further special property that I'll get to. But first, a Kähler manifold is a complex manifold with a Hermitian metric such that the associated 2 form is closed. So the 2 form in terms of the Hermitian metric is written like this, and its exterior derivative vanishes. And you can show pretty easily that it's actually, not only is it D closed with respect to the ordinary de Rham differential, but it's not D exact, it's not trivial. In particular, you can tensor copies of it together over cycles of suitable dimensionality, and they're greater than 0. So it's a volume measuring object on manifolds, or say submanifolds of your space-time. And because it's closed and non-exact, it defines a class in de Rham cohomology, more precisely in H11. So it has, because it has a holomorphic and an anti-holomorphic form degree. And a Calabi-Yau manifold further is a Kähler manifold that for a fixed Kähler class has a unique solution to the vacuum Einstein equations, or more formally is Ricci flat. So Calabi-Yau manifolds are Kähler manifolds that have a Ricci flat metric. It turns out that you can characterize a certain obstruction to whether a manifold can admit a Ricci flat metric for a given Kähler class in terms of the first Chern class of the manifold. So this is again another cohomology condition. And oftentimes we loosely say that Kähler manifolds with the first Chern class equal to 0 are Calabi-Yau. That just means that for a fixed Kähler class, within that Kähler class, there exists a unique Ricci flat metric. This was conjectured by Calabi and proven by Yau. Doesn't mean you have the metric. In fact, we don't have the metric for any compact Calabi-Yau, although there has been recent work in the past couple years actually finding an analytic, finding a solution to a Ricci flat metric for the K3 surface by Kotru and collaborators. But this is like brand new work. And for Calabi-Yau threefolds, we don't have analytic solutions in hand for the Ricci flat metric for a Calabi-Yau given some fixed Kähler class, which, as you can imagine, makes various computations very difficult to work with. So we have to go around. The existence of the first Chern class, I'll just mention, and I'm sorry that I don't have time to give more details on the geometry if these things are new to you, but this means that Calabi-Yau manifolds admit a nowhere vanishing holomorphic volume form. So a D, 0 form that in local coordinates can be written like this in terms of purely holomorphic coordinates. And this turns out to be unique up to scale. And moreover, it tells you that, say, for a D-fold, because these turn out to be unique up to constant scaling, tells you that the dimension of the cohomology, the D, 0 homology is 1. Cohomology is 1. Okay, so far we've only been working with perturbative things, and now I just want to propose some string dualities to you. I don't have too much time, so I'll try to throw in little details where I can, but we have kind of all the ingredients of the cast of characters, and I want to state some results and some dualities for you. The ways some of these string dualities were originally proposed were just by matching the number of supersymmetries preserved in a given compactification across several dualities. And then finding that the form of the corresponding moduli space of vacua for the different string theories compactified on these manifolds agree. So you can still kind of proceed by a KK type analysis like we did before, plug in, expand all of our massless fields in Fourier modes, see what we get, see what the massless fields or the moduli are, and then using supersymmetry, try to figure out locally at least what the moduli space of vacua looks like. And if the geometry in two compactifications are the same, try to propose that these things are dual to one another. There are other things we can do, like compute BPS or supersymmetry protected quantities and match them across dualities. And supersymmetry protected or BPS quantities and their mathematical structures will really be the focus of lectures 3 and 4. So today I'm just going to give you some results and propose them. And historically, this is kind of the way they were eyeballed and then later checked. Okay, so let's just do a little compactification on tori first of the type 2 strings. So we already saw the circle compactification, which is basically the simplest example of a tori. So remember, we had these left and right moving momentum vectors. Similarly for PR with the minus sign. And a more formal way of talking about these lattice vectors is that they themselves span an even self-dual lattice of signature 1, 1, meaning that the vectors can be given this Lorentzian inner product, any two vectors of this form, which is going to be PL, PL prime minus PR, PR prime, which depends only on the momentum and winding quantum numbers. Even though these momenta depend on the radius of the circle, the inner product depends only on these integer quantities. So this is an even self-dual lattice of indefinite rank, in contrast to the definite rank 16, indefinite signature, in contrast to the 16-dimensional definite signature lattices we saw for the heterotic string. And these descend from modular invariance as well. So in a d-dimensional torus, something similar happens when you do the compactification and impose modular invariance. You find that PL and PR, again, have to span an even self-dual lattice of signature D, D. And I'll denote that by gamma D, D. It turns out that any toroidal compactification on any choice of TD that you like, say a product of D orthogonal circles, can be obtained from a given one, like the orthogonal circle product, by an ODD transformation. So just with these orthogonal transformations of indefinite signature, we can go from our favorite torus and obtain a more general toroidal compactification, where the metric and the B field on the compactification geometry can change as we act on the left and right momentum vectors by these kinds of transformations. So here, of course, PL and PR depended on the radii. There are more complicated general expressions involving both the metric and the B field for higher dimensional tori, which I won't write down, but they're easy to look up. So these are analogs of Lorentz boost that are acting on these winding momentum lattice vectors, PL, PR. But on the other hand, we can rotate PL and PR by an element of OD cross OD, and the spectrum of string states will be completely invariant. And I believe you guys already saw some of these things in Sen lectures, so I apologize if I'm repeating things. And it turns out that there are further such boosts with integer coefficients that I'll label O of gamma D, D, that amount to just relabeling the states without changing the underlying lattice. So there are some lattice automorphisms. And this discrete group is often called the group of T-dualities for these more general toroidal compactifications. And this is this quotient space is part of the moduli space of a type 2A or type 2B compactification on TD. In fact, it turns out that type 2A and type 2B on a d-dimensional torus have the same low energy degrees of freedom, and you can relate them to one another by a single T-duality transformation along one of your available circle directions. So we saw T-duality along a circle last time, and in the superstring context, we just also pick up a minus sign on one of the fermions. And if you think about the product of all, say, the left-moving fermions, this defines the left-moving chirality operator. That's going to acquire a minus sign under this T-duality, and that's going to result in the GSO projection ultimately flipping a sign, and therefore preserving states of the opposite chirality that we originally had. So this innocuous minus sign flips our GSO projections from the point of view of the world sheet and exchanges 2A and 2B. And more specifically, these T-duality transformations, these kind of discrete Z2 T-duality transformations, are the elements of this orthogonal group that are that lie outside of the special orthogonal group. So kind of the disconnected parts.
Just a question.
Yes.
I'm a bit confused about the notation there.
Yes.
So is the T-duality group O gamma DD, or is the T-duality group the ODD are modded out by OD cross OD?
No, sorry. So the T-duality group is this discrete piece.
Mm-hmm.
This double quotient that I've written here is kind of the full form of the moduli space of vacua, accounting for metric and B field degrees of freedom, which I was about to come to. So this double coset space is part of the part of the moduli space of vacua that encapsulate the metric and B field deformations when you compactify.
Okay, so then the full quotient is ODD, then you mod out by OD cross OD, and then you mod out by O gamma DD.
That's right.
Okay.
So locally, metric and B field deformations can be written just as ODD mod OD times OD. So locally, you just have that kind of homogeneous space. And then there are further global identifications on the moduli space, like these T-dualities. And that forms the group O gamma D comma D. And we also quotient out by that.
Okay, thank you.
And indeed, it parameter this space without the discrete quotient. So this space parameterizes a choice of metric and B field, which respectively have the metric has D times D plus 1 over 2 degrees of freedom. The B field has D times D minus 1 over 2 degrees of freedom. And in total, we get a D squared dimensional space. That is the dimension of this moduli space that I've written down. And changing the metric and B field changes the string spectrum indeed. But in the type 2 theories, we're not done. We know there are also moduli coming from expectation values of the Ramon tensor fields with vanishing field strength. That changes the solitonic spectrum, if not the perturbative spectrum. And without being completely general, let me just give a quick example of how that can change the moduli space when you include those degrees of freedom. So let's think about type 2A on a T4, where we also have CM and CMNP. So you can turn on Wilson lines. And you also, so we have 4 parameters from here. So from Wilson lines on T4. And we also have 4 parameters from a choice of CMN and MNP. You can convince yourself that this also is some additional parameters. And we also have the dilaton, which we have not accounted for either. And it turns out that if we combine these degrees of freedom with the 16 degrees of freedom coming from the metric and the dilaton, it's not obvious that the fields should combine in this way, but it turns out that supersymmetry alone, considerations from supersymmetry alone, fixes the form of the moduli space to again be a double coset space of the exact same form, where the Ramon fields have now combined also with the dilaton and the metric and B field degrees of freedom into something that looks kind of simple, that looks very similar to what we saw before, but we've bumped up the dimensionality of this space. So it's not obvious that this happens, but it turns out to be true. The low energy degrees of freedom do get combined into a single moduli space component in this case. And in particular, elements in O gamma 5, that are not contained in the O gamma 4,4 from the metric and B field part, in particular, act non-trivially on the 2A dilaton. So this incorporates some non-perturbative dualities. And so in general, these kinds of dualities that combine T dualities also with the dilaton are called U dualities. So this is a U duality group for particular string compactification.
Natalie,
Yes.
5 minutes.
Okay. So I didn't get through everything that I wanted to get through today, but in the last 5 minutes, let me make a remark for later. And tomorrow I will say a little bit about Calabi-Yau's and mirror symmetry before getting into the mathematical stuff. So first of all, some remarks that are, well, they're relegated to remarks since I ran out of time. A similar analysis goes through in the heterotic string. But we have our 16 Wilson lines from our extra gauge fields. And that augments the moduli space as you might expect. We get some D times D plus 16-dimensional moduli space. This turns out to, and again, it turns out to be quotiented by an orthogonal group of the appropriate signature. And the lattice vectors, again, take values in an even self-dual lattice of the corresponding signature. And even self-dual lattices with the signature are unique, as it turns out. So we have the same perturbative moduli space for either heterotic string theory, E8 cross E8 or SO32, as well as for the type 1 theory, it turns out. So once you compactify the E8 cross E8 or SO32 heterotic string theories on a circle or a higher dimensional torus, they become isomorphic or T-dual to one another. So this is T-duality of the heterotic string theories on tori or circles. Okay, so let me make a final remark, so I don't run out of time. Let me think about just a 2 torus. As you've seen in CFT and other ADS CFT and other contexts, a single 2 torus, a complex torus can be parameterized by a variable tau in the upper half plane, up to SL2Z transformations. And tau parameterizes the complex structure of this torus. We talked about complex structure last time. Roughly speaking, it governs the shape of the torus. But we also have Kähler forms and B field degrees of freedom, and those can be packaged into a complex 1,1 form, the Kähler form, the complexified Kähler form, if we incorporate our B field. And in the case of a T2, it turns out we can rewrite it a little bit more suggestively. I'll skip the details, like this, in terms of a new modulus sigma that sits out front, where sigma has the property that if I integrate it over the 2 torus, or if I integrate the Kähler form over the 2 torus, I get 2 pi I sigma. So the imaginary part of sigma is the area of the torus, is the area. And since areas are positive, sigma also takes values in the upper half plane. And indeed, the automorphism group in the 2,2 case splits into SL2Z cross SL2Z with an extra Z2. So the 2 SL2Zs act on sigma and tau independently, and the Z2 exchanges tau and sigma. It exchanges the complex structure moduli and the Kähler moduli. And this is nothing but T-duality. So in fact, it is a low-dimensional version of mirror symmetry, which will be the focus essentially of the rest of my lectures. So for example, if we just think of the simplest 2 torus as a product of circles, then tau, orthogonal circles, then tau can be written in terms of the 2 radii like so. Sigma can be written in terms of the 2 radii like so, clearly computing the area and then the shape. And a single T-duality on one of the S1s is going to invert one of the radii. And so very clearly tau and sigma are going to get exchanged. So this is a preview of mirror symmetry is T-duality, even on more general Calabi-Yaus, as we'll talk about next time. And that means it actually has a very simple worldsheet implementation, and we can get very far by studying the supersymmetric worldsheets with targets mirror Calabi-Yau manifolds, and we'll talk about all that next time. Okay.
Wonderful. Thank you. All right. Perfect timing. All right.
It was either stop there or go on for another 20 minutes. So
I've
you
never,
have to make the hard
never
calls.
seen you deviate by more than like half a minute. All right. Questions for Natalie?
Can I ask a question?
Please.
My question was about what you said about the not having these metrics available. I think this was for the Calabi-Yau manifolds.
For compact
Oh,
Calabi-Yaus,
compact.
yes.
Okay.
Which
Okay,
is all
sorry,
I'm thinking about in this lecture.
Okay. I don't know a lot about this. So my question was, what's the obstruction to finding these? Like, it's just exceedingly difficult to calculate, or
it's exceedingly difficult. People are able to make numerical approximations to Ritchie flat metrics.
Okay.
There are numerical approximations, and some of them are pretty good. But analytically, the analytics of writing down a metric and proving that it's smooth and Ritchie flat is extremely hard. So people have tried to start with some simple metric in the same Kähler class and try to deform it to the unique Ritchie flat metric that Yau's theorem tells us exists, but it's just incredibly difficult. And I don't have a full appreciation of all the mathematical reasons why it's hard. But I should say that in the case of K3, which is the unique non-trivial Calabi-Yau twofold, papers in the last year or two have been proposing expressions for a Ritchie flat metric on K3, and those are using string dualities, ones that I haven't talked about, but other more exotic string dualities in a really really crucial way.
Could you provide a reference to one of those papers or so in your notes?
Yeah, absolutely. Yeah, they're referenced in the type notes, which I haven't posted yet because they need a great deal of cleaning up and I need to fix the broken bib file. But I can post them in the Slack also this evening.
Cool, thank you.
Sure.
Other questions?
This may be a very naive question, but could you go over the reasoning for that double quotient group? I got confused and I'm now not understanding what's the logic behind it.
Yeah, I went through it a little bit fast, and some of it, the argument that I'm giving is much more of a plausibility argument for why you might think this is the right moduli space than an honest to goodness derivation. There are better ways to justify it. And a lot of it involves, the supersymmetry of the effective theory can constrain the form of the moduli space quite a bit, at least locally. In the torus case, actually, we know the form of the moduli space globally. It is this double quotient space. So you can get farther with some geometric arguments mixed with some constraints from supergravity that I haven't told you about. But what I told you about, kind of more from the worldsheet point of view, was I have some general left and right moving center of mass momentum vectors. So those are functions of, in general, the metric and the B field, quite analogously to how in the case of the circle, they depended on the radius. More generally, they'll depend on the metric and B field of the torus. And you can write this in terms of these left and right moving vectors. You can also compute the spectrum of the compactified string theory. So these vectors, because of the constraints imposed by modular invariance, turn out to span an even self-dual lattice. It's gamma D of signature D comma D. And you can ask sort of what, okay, so then you want to ask sort of how can I relate different toroidal compactifications to one another by changing the metric and B field, which correspondingly is going to deform these lattice vectors into one another. And it turns out that, if you start with any particular metric and B field, with some corresponding set of vectors, you can obtain any other toroidal compactification with a different metric and B field by acting on PL and PR by an OD comma D transformation valued in R. This is like Lorentz boosting your lattice around. But some of those OD comma D transformations turn out to not actually change your compactification. In particular, the spectrum and string theory will remain invariant under the transformations that are a product of OD cross OD that act on the left and right moving parts separately. It's not that hard to see that those are trivial transformations. So when we're spanning the moduli space of all possible tori compactifications, we want to get rid of the transformations that act trivially, that don't actually change our underlying compactification, because the moduli space is about spanning the possible non-equivalent physical compactifications that we have. So we quotient out by the OD cross OD part that it's not hard to see that those transformations leave everything completely invariant. And then further, it turns out that there are additional transformations that form a discrete group that also lead to equivalent physics. So unlike the trivial transformations OD cross OD that are just kind of manifestly, like obviously trivial transformations, these other transformations, the discrete ones, that provide interesting global identifications of the moduli space are duality transformations. And they turn out to take the form O gamma D comma D, or automorphisms of this even self-dual lattice. They are automorphisms of the lattice, so they turn out to leave the physics invariant. But they're global. They're not so visible by just locally looking at little deformations of the metric and B field. So they constitute a further quotient of this symmetric space. And they include like our T dualities.
Yes. So essentially, what that group is telling us is like, okay, we have this moduli space. We know it. The ODR should bring us between the different B fields. We can mod out by the trivial ones, and then there's some non-trivial global things, which are T duality, which are the symmetries of this even self-dual lattice.
Yeah, if you like, they're the non-trivial symmetries of the string theory. They include T dualities. And and in special cases, when they combine the other degrees of freedom, they include U dualities. So that's like, so U dualities are like S dualities plus T dualities. I think you guys have already seen S dualities, so I apologize that I didn't introduce it in my lecture, but it's inverting the dilaton, the axio-dilaton, tau goes to -1 over tau, transformations like that. The U dualities are combinations of S and T dualities. And some moduli spaces still have this form, but now the lattice automorphism group is a U duality transformation. It's actually mixing up the perturbative and non-perturbative stuff in a non-trivial way.
Okay, thank you. That helped a lot.
Excellent.
Can I ask a
Yeah,
question?
go ahead.
So in the context of n equals 4 supergravity, I've seen that so when they write it as a compactification of heterotic string theory, I've seen that they write the moduli space as OD comma D comma Z. So is it after you quotient out with the T duality subgroup that you get the discrete version?
So the T duality subgroup is part. The T dualities are part of this O gamma D comma D that I've written out. Some people prefer to write the same group as O D comma D Z, the Z valued, but I don't like that as much because there can, I mean, at least to my understanding, the more correct way to specify that discrete group is as the automorphism group of the lattice O gamma D comma D. Some people kind of write these are integral transformations. They're transformations of a lattice. That's an integral object. I don't like writing the T duality group that way. I think it's a little bit misleading.
But
does that answer your question?
Yes, yeah. But would it be fair to say that they both describe the same group?
When they're written down that way in papers, they are intended to describe the same group. But you should really think of it as the automorphism group of the lattices, not just arbitrary OD comma D matrices with integral entries.
So I think what you're saying, does that mean you So I think the reason why the Z appears is because you have to also satisfy the Dirac quantization condition for the Q and the P electric and the magnetic charges.
Mhm.
So is it when you impose the OD, D, Z and also demand that you have to satisfy the Dirac quantization? Does that become equivalent to what you are describing here? Because that's some additional constraint on the charges.
Yeah, that's a good question. I'd have to think about the group theory of that for a minute, just because I don't usually think of the group that way. I prefer to think of the lattice automorphism group. So the answer is I should think a bit and get back to you. My gut feeling. Well, okay. Let me not say anything. But
Right. Okay. Thank you.
Any other recorded questions? Okay, so then let's thank Natalie again and